I claim that if we have a monotone function, the discontinuities are at most countable. So just for the sake of argument, let's suppose our function is this one. These are the discontinuities. And it's monotone increasing. So define E to be the set of discontinuities. So E would be all these guys. That would be right. Okay. I need a lemma. The lemma is this. If X is in E, then the limit from the right, which I'm going to denote by that, and the limit from the left, which I'm going to denote by that, exist. They certainly exist on that set, right? Right. F is continuous on the complementary set.
These are all kind of discontinuities.
We don't know that yet. But monotonicity is enough to do that. You know, you can't have the thing zooming off asymptotically because, you know, it's bound. It's bound. If this is, let's just take an interval AB here. Okay, AB. F of B bounds all of these values. If it's monotone, it can't shoot up asymptotically and get back down and pick up the trail again, right? We're going to use that fact. If it's asymptotic, if it's monotone, it's bounded. So it can only behave poorly to some extent. Okay. You know, you can't have the salt and pepper function here. Keep popping it down. You can't do that. Just being monotone is enough to have lateral limits in every discount. So that's the first order of business, is to show that lateral limits exist. Specifically, this is what happens. The suprema of F to T, if I pick T between A and X, is equal to the left-hand limit, that's this thing, right? So I come in from the left to the minus values. That's going to be less than or equal to the value with X, which is less than or equal to the right-hand limit, which is the infield of the F and T's as I go out the other side. So if I let T be bigger than X, all the way up to B, I have that. So that's the condition that I'm saying exists. So that's the first thing I'm claiming is alpha, that these two things exist. And the second thing I'm claiming is that if A is less than X is less than Y is less than B. So like if X is here and Y is here, then the following thing happens. The right-hand limit of the lower guy is never greater than the left-hand limit of the upper guy, right? So the right-hand limit of the lower guy comes in from there. The left-hand limit of the upper guy is there. You can't see everything. This is the condition algebraically. This is the condition on the graph. The limit from the negative side of Y dominates the limit from the right of the lower guy. All right. So to show that, we note, first of all, that the set f of t, where t is between a and x, is bounded above by what? F of x? It's monotone increasing, right? So f of x is going to be the king there. It's at the top. I have a bounded set of real numbers. What can I assert using the LUP axiom? Completeness axiom. At least upper bound axiom. What can I say? Something exists. Therefore, A equals the soup of the f of t's, the soup between exists. Okay? All right. I want to show, I'm a big one for writing down what it is. This is a note to self in the middle of the proof. What the hell am I trying to do? Because sometimes you lose track of that. I want to show that, as a matter of fact, A is the limit from the left. Remember the picture? I'm sneaking up on x here. It doesn't, well, an x is, I'm allowing it to be now. I'm allowing it to be one of the points of this continuity. So I'm sneaking up from this side. And there's an LUB, which is A, and I want to show that A is in fact the supremum of the f of t's for t below x. Okay, so that's what we'd like to do. Why is this true?
K is less than x.
Well, it's less than x if the thing's monotone, so this has to be true. Okay. Let's fix epsilon. That's always a good idea. You can't think of anything else. Write that down. Fix epsilon. Okay. Since A is the least upper bound, there's a delta greater than 0. Such that the following sort of thing happens. If I am between A and somewhat less than x, all right, then we can arrange things that f of x minus delta is less than or equal to A and greater than A minus epsilon. Why is that true? We have monotonicity and we have A being the soup of, what was it? The f of t's between A and x. The soup has the property that if you back off it, there's a value of t that makes f of t in there, right?
We consider x minus delta.
Yeah, that's what it is. This is t.
And A is all f of t. So it's got to be greater than
If you take a little, shave a little bit off x and drop that for n, if you fix epsilon in advance, it's possible to find a delta that is small enough so that, x minus delta is pretty close to x, but it's before it, so this function's monotone. So f of x minus delta is going to be certainly no greater than A. We're allowing for the possibility that this is weakly monotone. Could level out, but it never goes down. Could level out, never goes down. So I'm above A minus epsilon and certainly not above A. Okay? Okay. You want a picture of that? Send it to me. So here's this is epsilon. This distance here is epsilon. And this is A, this level. So this is A minus epsilon. This is x, and delta is this distance here. So x minus delta is here, and my function evaluated there is certainly no greater than A, and greater conceptually, right? Okay. So, by monotonicity, we have the following. We have x minus delta less than t less than x implies f of x minus delta less than or equal to f of t less than or equal to k. And from that we can conclude that's just the monotonicity condition. Weak monotonicity. If you move to the right, you're certainly no less. That's what weak monotonicity is in principle.